Welcome everyone to this new session of the Barcelona Mathematics and Machine Learning Colloquium Series. This is an activity organized by the Autonomous University of Barcelona, and we have in mind all the other research centers and universities, not only of Barcelona, but also the people who join us from all over the world. This is an activity in which we focus on what are the mathematics behind machine learning and what can machine learning do for mathematicians, which is actually the topic of today. We do that 3 times a year online. Questions are welcome. You can raise your hand and there will be discussion at the end of the lecture. And the most important for us is who does that. So this year we had already Adi Shamil. Today we have Carlos Simpson. We'll close with Charles Pfefferman. Let me introduce very briefly Carlos. So Carlos did his PhD in Harvard University, and then he's working for the Université Paul Sabatier in Toulouse, and he's currently in Nice, now as a professor of the CNRS. He was an invited speaker in the ICM of 1990. He got in 2015 the Sophie Germain Prize, and very recently he started this ERC Synergy project, this Malinca project he will mention today. So Carlos, thanks a lot for accepting our invitation, and the floor is yours.
Okay, thank you very much for the invitation, the opportunity to participate. It's very interesting. I think I need to reshare the screen, right?
Correct, yeah.
Okay, is that good? Let's see now. Let me try to do this in full screen.
Yes.
I know.
Yes, we see
wrong one. Sorry. Okay, is that good?
Yes.
This may be slightly better. Okay, are we ready to go?
Yes, please.
Okay, thank you very much for listening. And so I'd like to talk about reinforcement learning for proofs, which is things I've been thinking about for more than 5 years now, 5, 6 years. Jump right in. So this is the part of, it's one of the topics of our ERC Synergy Malinca project. So we'll get to that in just a second. So let me just say that the computer formalization of mathematics has recently come into a lot of focus, I think, for the wider mathematical community. But this has actually been going on for quite some time, and myself, I was in contact with this around the year 2000, 2007, between 2000 and 2007. I saw that you have Charlie Pfefferman, who will be speaking next. So I didn't put this on my slides, but actually, when I was in Princeton, I was in Princeton. You could have added, but anyway, when I was in Princeton, I was heard about this from Sergio Kleinerman and Rafael de la Llave, sorry, who were working with Charlie Pfefferman about computer formalization at the time, which was a really long time ago. So they told me about that at the time a long time ago, and it sort of stuck in my mind, among other things. Anyway, so now the advent of artificial intelligence, machine learning, that kind of thing, has obviously opened up the prospect of making proof formalization more available for mathematical reasoning. And so what we're going to look at today is the general problem of reinforcement learning for automated proofs. And this is an aspect of our Synergy, Malinca Synergy project. However, unfortunately, I don't have any new stuff to report for that, really. So I'll give some general aspects about that. And then I'll specialize to the more specific examples that I've looked at so far, which are, there's some kind of proofs, but they're sort of specialized kind of proofs. So I just don't want to mention all the people who I would like to thank, because I will surely forget some, and I don't feel like forgetting anybody. So let me just say thank you to all the people who have contributed discussions to this project. Here's the page with the members of the current members of the Malinca project team, including the PIs who are Paul Méliès, Hugo Eberlin, Philippe Picout, and myself, and also junior members, including David Alfaya in Madrid, who you might know. Anyway, so yeah. So our project is called, the long title is Mathematica e Lingua Franca, which means the lingua franca of mathematics. And we can remember that the lingua franca was the simplified language in the Mediterranean basin in the Middle Ages, maybe, and probably before that, that was designed to allow communication between people that had different, home languages, but needed to communicate for economic and commercial exchanges. And so the idea behind the title of our project is that we're faced with a somewhat similar situation of mathematical communication involving different entities, including mathematicians and computers, but you might see even probably many different computer languages and stuff like that. Not to speak, of course, of different mathematical theories too, which could also be the topic of the question. And so you'd like to have a similar situation where you have some kind of common ground where the communication can happen, but it has to be simple and it has to be precise, basically. So one of the main aspects here, of course, is the formalization and verification of computer proofs, which is a classic topic. So let me just mention a few things, which are ROC, which is the new name for the COC project, Lean, Isabelle, Mizar, MetaMath, Agda, and others. And automated proof, there's a whole list of programs I should put here, but I just put Vampire because that's the one I know about a little bit. I had a student who wrote his thesis about that. But there's a whole bunch of programs who actually participate in contests every year to prove kind of specialized first order logic instances, and that's made a big advance in that theory. And those intersect a little bit with the proof verification programs, notably with the sledgehammer tactics, which are available in some cases, which we'd like them to be more commonly available. But anyway, okay. Then of course the Malinca project has a linguistic aspect also because we're trying to treat mathematical texts. And here again, an exact approach to linguistics is not really necessarily feasible on the overall scale. Of course, the large language models, ChatGPT, whatever, those are taking kind of a probabilistic approach and have, of course, made great success in that way. But to have any kind of exact approach, you wouldn't expect to have that for all of natural language. But we're sort of thinking at least that that if you take the subset of natural language that's used to express rigorous mathematical writing, by which I mean, inside a text, of course, there might be some non-rigorous parts, of probably many non-rigorous parts, but the rigorous parts that the author thinks are supposed to be precise, those are going to be a subset of natural language, and that might well be more adapted to exact methods of analysis. And then the intermediate language, the lingua franca, as it were, is supposed to be thought of as a bridge between the written texts and the computer formalized mathematics. When we say that, that's a sort of an oversimplification right away, because you should really think of a whole range of different intermediate stages, essentially. Now, this is all this whole thing is really strongly based on type theory, because logic these days is most often expressed in terms of Russell's type theory, which was originally introduced as a way of resolving classical paradoxes, Russell's paradox and so on. And it found its way quite quickly into computer proof verification. So it was the basis for automath, de Bruyn's automath in the 1970s. And so a nice note that we can make here is that computational linguistics can also be based on type theory. It doesn't necessarily in all cases but some versions are based on type theory. So you could hope to have use type theory as a sort of a common framework for those two. Okay, then if you want to apply this to mathematics, then we will need to study some kind of look at the logical foundations, how you want to implement the foundational structure of mathematics. And this is going to have an impact on the efficiency of the programming. So this is one of the themes of study, and other themes I'll just mention here of the project are things like homotopy type theory and other synthetic reasoning systems, things about the geometry of reasoning, how to view reasoning steps as in some geometric way, which would allow you to to refine like search questions, for example. Game semantics for proofs, which is kind of an obvious and in some way a relationship with the computer, with machine learning, in the sense that, you know, we've all heard about Go, which is, you know, AlphaGo or AlphaZero and so on, that are AI stuff that's used to treat games. So you would obviously think, you know, if it can deal with Go, it can probably deal with some simple mathematical proofs. And so game semantics is an element of that. Then there's questions about translations between different representations. So we might not have chosen a single axiomatic foundation, but maybe several. Or, for example, if you see here a homotopy type theory, you might want to translate that back into regular topology, for example. Then the whole formalization process is going to be interactive and bidirectional, rather than, you might say, the first thing I said a couple slides ago was just we want to translate from mathematical text to formalization, but you really need to be able to go back and forth. So these are a bunch of topics in the project, which are not really going to be topics of my talk today, but I just wanted to mention them. Okay, so if we think of a natural language mathematical text, you know, think of your favorite page. Oh no, I think I may have made a mistake. Can you guys still see my screen?
We see searching for proofs. Yeah, in a natural language mathematical text.
Yeah, okay, sorry, I did something on my computer, but okay, we're good. Yeah, sorry about that. Thank you. Yeah, so if you think of your favorite page in a mathematical text, how are you going to turn that into a formalized proof? Well, there's a whole bunch of details which the author didn't actually prove. Things like, you know, is your element of your group, is it an element of the subgroup, that type of thing, which you need to actually formulate and state and prove as sublemmas or something like that, you know, or at least claims within the proof, to make a document that's accessible to the computer verification system. And this is one of the main obstacles to formalizing lots of mathematics, is that it takes a lot of work to fill in those details. So we'd like to be able to have a kind of a layer in this whole sequence of layers, intermediate layers, which would be aimed at filling in some of these small steps. And the utilization of AI or machine learning comes to mind. As we'll see in a little bit later, it's not completely clear whether that's going to be the only possible option. Maybe other types of proof search algorithms could be also helpful or better. And let me just say, I mean, I think you all probably know by now, there's a ton of recent research coming out, math.inc, Joseph Urbon had a preprint in January. I mean, tons of stuff all about that, which I'm not going to try to write down here. Let me just say that according to what I've said so far, you can see that there's a small, maybe subtle difference, but might not be completely trivial, between what we're trying to, what our aim here that I've described is, and these things that you might have heard about training LLMs to solve math problems, like math Olympiad problems and stuff like that. Because in fact, we're not actually trying to ask the computer to find any kind of clever new ideas. Whereas, of course, if you're trying to do a math Olympiad problem, you have to be pretty clever. And so in our viewpoint, that's going to really be the work of the human author of the mathematical text. So we're really not trying to replace humans here, which might be different from some companies or something like that, possibly. So we're just trying to assist the mathematician by dealing with the lower level work that you would need to use to go between the standard written mathematical text and a formal proof document. And so that's not completely identical to, of course, has a gigantic overlap, but not completely identical to what some of the projects that are happening are working on. And of course, we would like the process to be transparent and reproducible, which again, you might say it could differentiate the whole system from what some of the things we've heard about. That's a goal. Okay. So now the topic for today's talk, we'd like to investigate how machine learning can be used, and in particular, what's called reinforcement learning, in order to find proofs inside a controlled environment. I don't have anything current to report on the the type of proofs that you would want to use to fill in mathematical text. Not extremely advanced so far, but have some ideas. But so I'd just like to discuss what I've done so far, which is on the general framework of the question. I mean, it's always going to be pretty similar. And then we'll look at the example, a couple of examples involving proofs for the classification of combinatorial objects. But the idea is that, whatever happens with proofs, mathematical textual proofs is going to probably be quite similar. So I just wanted to have a brief discussion of the whole mathematical proof question anyway, to start with, without having any real results here. But my own personal taste goes more towards the untyped direction, following the Zermelo-Fraenkel axioms for classical set theory, which has, whether you like it or not, has been really the main foundational basis for pure mathematics in the 20th century. And there's really no obstacle to implementing this completely in a proof assistant. You would have a type E for sets for ensemble. You have a basic relation of elementhood, which is maybe denoted inc. Then the subset relation would be defined to be for all x, for all sets x. If x is an element of A, then x is an element of B. That's a subset of B. And just continuing from there, you can just imagine developing set theory, and I've done this on several occasions in different ways in the Rock theorem prover. Now, what about the structure of a proof in general? So, then if we think of a typical proof that you might do within set theory or other types of proofs, a proof is composed of steps, and when you think about it, the time in the proof is actually a tree. We'll see why in a minute if you don't see. So each time in the proof corresponds to a node in the tree. And at a given node, there's the context. So for example, if you're familiar with proof assistants, that's going to be the context window in a formalized proof system. The root of the tree is the global context that we're trying, which is to say the thing we're trying to prove. Then you could view the tree as being built up successively in steps, where the leaves of the tree, the bottom nodes, are divided into 3 groups at each step. 2 of the groups are similar, if not possibly the same, namely either done or impossible. We'll see in the classification situation, done means that we got some kind of new information, and impossible just means that that branch was closed off because it wasn't possible. And then active, those are the ones where some further discussion is needed. So in the logical case, done and impossible will really be the same thing. There's not going to be a distinction in that case. It just means that the conclusion false has been found. Assuming, for example, we're doing a proof by contradiction. So you put the thing you're trying to prove, you put its negation into the context at the start, and then you try to prove false from there. So any branch that proves false is just discarded right away. In the case of a classification proof, done means that we have to have we found some objects in our classification. Impossible means that we didn't find any objects. So in that case, it's interesting. It's useful to have that distinction. If you found some objects, you need to put them into memory as to your list of objects. Then when you have an active node, that means that there's a proof step that requires an action. Okay, and of course that's the game aspect of the whole thing, is which action to use. And a given action is going to generate one or more new nodes below that node. Those nodes themselves will then be classified into active, done, or impossible. That's how the tree is built. So at a leaf which is active, if you make a step which uses an action, then the action adds new leaves below that leaf, and that node becomes an interior node of the tree. So as an example, if you've used proof assistance, you know that sometimes when you do some step, it might generate several subgoals instead of just a single subgoal. Those several subgoals, those are the different new nodes below that node. So just as a typical example, which is kind of a general example in some way, if we apply the excluded middle on a proposition P, that means we assume that means you can say, for a given thing P, you can say either P or not P. That creates two new nodes, one in which the context has a P in it, and the other in which the context has not P in it. And now the proof is divided into two separate subproofs. So that's the basic idea. Now the question for an agent who's doing the proof, either human or machine, is which action should you take at each active node? So in the previous example, you can choose the proposition on which you'd like to apply the excluded middle. So which one would be a best one to choose? I mean, there might be ones that are completely irrelevant, and that doesn't help you at all. It just doubles your proof size. And there might be other ones which are like exactly the thing you need to know, and so that works well for the proof. So so you're going to have a problem of trying to figure out which action to take. In a more tactics-based proofs, then it just means which tactic should we choose. And as we'll see in a minute in the combinatorial proofs, the thing about the combinatorial proofs is that the set of actions is pretty closely delimited. So it's not easy to understand, and there's not too many of them, and so on. Which is different if you have to like just choose some term in some gigantic infinite collection of terms. That's not a very small set of actions. So in some way, this picture is going to work better if we can limit the size of the set of actions to choose at each point. But in any case, if we choose an action, that's going to have an impact on the size of the proof. So the total number of nodes, and what's the size of the proof? The size of the proof is the total number of nodes in all the proof until we're finished, which finished means that all of the leaves of the tree are either classified done or impossible. There's no more active leaves. If there is an active leaf, then you have to treat it. Okay. And so there's a reinforcement learning problem, which is for a given context associated to an active node, what's the best action to choose in order to complete the proof as quickly as possible? Now, we're going to describe here a first scenario, which is structure classification of combinatorial structures, and in fact, the simplest type, which is semigroups. But I just wanted to comment that, a lot of work has been done on proof searches for classical mathematics statements. So this Mizar, Lean, Kog, Rock, I should say, Isabel have various different types of automated proof techniques. And first order theorem provers such as Vampire and its other, I should probably have mentioned, but its other competitors are obviously dedicated exactly to that question. I had a student who wrote his thesis about that question, Boris Schminka. Nonetheless, the general setting is pretty difficult, so we're going to work instead in a somewhat more limited setting, which is the classification of finite structures. And so we'd like to so here the problem is to classify or to enumerate the instances of a structure. And that can be seen as a type of a proof. So the context associated to a node is then a collection of constraints on the operations in the structure that we're looking at. And then the steps correspond to making cuts on those contexts and choosing different choices. Okay, this setting is actually useful for this whole experimentation with machine learning, because the all the different steps you can choose each stage are pretty much the same, or at least similar. Not too difficult. It requires some doing, but still programming the results at each proof step is going to be relatively straightforward. And it also generates large quantities of data. So since we're talking about classification of things where there may be like tens of thousands of examples, for example, then you get lots of data, and that's useful to train the machine. It's going to be difficult to do machine learning on something where you only have like 3 pieces of data or something like that. So these were the reasons that sort of motivated this choice of topic. And so here we just you could do other more complicated structures would obviously be interesting, structures with several operations and so on. The simplest case is the case of semigroups. It's an equational theory with a single binary operation and a single equation, which is associativity. It's already not so easy. So let's just recall a semigroup is a set with a binary operation subject to the associativity axiom. And we'd be interested in classifying the finite semigroups of the given size, maybe with some other constraints also. The counting question has been treated for size up to around 10. Because I haven't seen recent references. I would be surprised if that hadn't been extended to like 11 or 12 or something like that by now, but I haven't heard of that either. The group of authors, I think, led by Distler, by Andreas Distler, and plus other authors, they gave the solution up to 10 at least, and also provides precise formulas in what's called the 3-nilpotent case. Then after the 3-nilpotent case, which you'll see what that is, what that means in just a second here. After the 3-nilpotent case, the next case to look at is the 4-nilpotent case. Okay, so in the 4-nilpotent case, it means that any word of length 4, the product of any 4 elements is equal to 0. Of course, the 0 element in this case is uniquely determined. You could think of it as a 0 array operation in the signature if you like, but it's also just the product of any 4 elements is that thing. And then you can make a 4-step filtration whose last step consists only of the 0 elements. And then what we can do is we can think that we're in the world of F1 algebras. Algebras over the famous field with one element, if you're into that sort of thing. And then kind of take the associated gradient of this filtration. What that amounts to saying is that I'm just going to write that down specifically here. We just make a few constraints. And going from the general case to the associated graded case and back involves a question of lifting stuff, but there's not really any constraints on that lifting in this 4-nilpotent case. So those are, in the 4-nilpotent case at least, those are pretty much, roughly speaking, equivalent. I mean, if you have the list of things, I mean, to isofilter everything is not a very straightforward task, but assuming you have just like a list of all the elements of all the structures, then you'll be able to get a list of all the, if you have a list of all the graded structures, you'll be able to make a list of all the ungraded structures pretty easily. Then of course you have to isofilter that, which is not so easy, but just for, and that's really the only thing we're talking about now really is just creating the basic list of the structures. So in the graded case, then the A, B, and half of I are the graded pieces of the filtration. And it means that our semigroup has the form of a disjoint union of A, B, and I, and that the multiplication operations send A cross A into B adjoin 0, and A cross B into I, and B cross A into I. I is really the 3rd and 4th graded step put together. Okay, so in this case, what are we simplifying here? What we're simplifying is that the multiplication operation A times A is not allowed to be equal to 1. It's allowed to be equal to 0 or something inside B. But we're saying, okay, if it was equal to 1, we would just set that equal to 0. It would be the same. Okay. So let's let little a be the size of A and little b be the size of B. And we'll call this graded with ranks A, B, 1. Then the overall size, the 1 is the number 1 element, not including the 0 element. So the overall size is n equals A plus B plus 2. So this idea of associated graded comes from thinking of things as F1 algebras. And if you, the operation, I mean, but the basic operation is that if you had a filtered object but not graded, it means that the multiplication A times A could be equal to 0 or 1. Just means every time it's equal to 1, you just set that equal to 0. That in this case, that amounts to taking the associated graded. That's just to simplify the computer stuff. Okay. So if we go back, well, let's see, I should go back here. Right, this operation phi, for example, A cross B into I. The table is a table of size A times B filled with 0s and 1s. There can be a lot of symmetries, and one of the big problems here is that neural networks kind of don't like symmetries, basically, as a general remark. When you have something which has a lot of symmetries, basically, you're asking the neural network to learn the symmetry at the same time that you're asking it to learn about the stuff you're looking at. And that just takes a lot of effort, basically. And introduces lots of places where it can just go wrong, essentially. So you'd like to remove as much symmetry as possible. And so one way to do that is to just take the equivalence classes of all possible tables. For the sizes A, B that we're talking about, there's not that many possibilities. Choose a set of representatives and then fix. So we fix one of those tensors. We fix the tensor phi. You still have some non-trivial symmetry groups, typically Z2 or Z2 cross Z2. We could also try to fill in some elements of the opposite table, the transpose table psi, as to break these symmetries. And so we can choose a set of initial conditions in that way, rather than just the full question as initial conditions. That just makes it smaller to be able to treat. I mean, we can treat a larger case of the proof, but restrict it in that way. So now I wanted to explain a little bit about how to program these structures in PyTorch. I think this is part of the interesting thing that's happening here. PyTorch is a great language, basically the same as NumPy, as far as I understand. It sort of has its advantages in that it has a kind of a closed structure of everything works together perfectly well. And in particular, in terms of transforming things from one type to another, I mean, since all the structures in PyTorch are all the same type of structure, then they're sort of automatically living in the same world, basically. And also the neural networks are also programmed in PyTorch, and you have a standard functions and stuff like that. So it's easy to go between the combinatorial objects and the neural networks. So now what's a proof context? So a proof context, we could think of that as a template. It's going to be a three-dimensional Boolean tensor of size n cross n cross n, which we'll call prod or rho will be the terminology I'll use in a minute. And the meaning of that is that prod x, y, p equals 0. That means that x times y is not equal to p. Okay, x, y, and p, those are things in the set of size n, from 0 to n minus 1. So this is a tensor determining when, what are the possibilities for the multiplication operation. And prod x, y, p equals 1. That means that x times y might be equal to p, but not necessarily. Okay, so the case where you have a 0 that's the case where, false. That's the case where you have some information. The case with a 1, that's not really any information. Okay, the initial position of the proof is if we don't include the nilpotent hypotheses and so on, the initial condition of the proof is just the tensor with ones filled in with ones. And so let me just comment here. The 0th dimension of this tensor, which here has size 1, that's what we would call the batch variable. And that's one of the nice things about PyTorch is that it allows us to treat up to like 1,000 proof positions all at once. So the initial position for just an arbitrary semigroup of size n is going to be just n cubed tensor filled in with ones. So in practice, as was described above, we're going to actually be refining the initial position so we can choose some stuff. So for example, if we divided the n into segments called capital A, capital B, capital I, then that involves putting a blocks of zeros into this tensor. And then even also, if we chose the phi thing to be a certain thing, for example, that would be just filling in that block with some zeros and some ones. So that's going to be the thing. That's going to be the tensor that goes at the root of the tree, basically. Now what does it mean for a value to be impossible? Because it means that we're looking for x times y equals p, right? So that means that p has to be something where there's a 1 in that column. So if there's a 0 if there's any one value of xy such that the column xyp is empty, that is to say there's no values of p, then that's not possible. So in PyTorch language, being possible means that any of the third variable dot all of the second variable dot all of the first variable This is now a tensor in the 0th variable, which is this is a Boolean tensor in the 0th variable, which is the batch variable. That's going to tell you all the things in the batch where that template is possibly a template of a semigroup. And impossible is not possible. So these are going to give us Boolean tensors whose length is the batch size, telling us when it's possible. Then similarly, okay, if you think about it a little bit more, what does it mean to be done? Done means that we found a single semigroup. Okay, so that means that there's exactly one value of P such that prod xyp equals 1, and all the other ones are equal to 0. And we can do that by just taking a sum, which is to say, taking prod, which is a Boolean tensor, turning it into an int64 tensor, summing along the 3rd variable. Then done means that stats equals 1 for all of the 2nd and 1st variable. Okay, that means for all xy, there's exactly one value of P such that that Boolean tensor is true, and the rest of them are false. That tells us that x times y equals P is the one with the property that prod xyp equals 1. Then, of course, you would also want to verify. I mean, normally you've done things in such a way that that's automatically verified, but you would re-verify, of course, that the associativity condition is satisfied. It's also possible in some cases. In some cases, it turns out in these nilpotent cases, sometimes you might have several values of the possible values of multiplication, but it turns out that the triple products are always the same, and they're the same for the left and right parenthesization. That means that any choices of the semi-grouping within that template will always be associative. So you could call that done if you like. Isofiltering is a different matter, which we'll not really discuss here. In other words, you want to take the things that you found and then mod out by the permutation group, so that to try to figure out what's the to isomorphism in the list of things that you found. That can be done. Now the main step here is processing. So it means that for a given template, the associativity condition is going to add some additional zeros, namely additional information. And the nice thing about this is we can program this directly using PyTorch Boolean tensor operations. So let me just explain how that works. Finishing pretty soon here, but so just very quickly, so you need to expand. So this length thing, that's the batch variable. Then now we're talking about tensors of length 1, 2, 3, 4, 5, batch plus 5. It's this. That's the set of all I for the batch variable, then x, y, a, z, and p. And a is a new variable representing x times y. So if we take prod, which has size n, 1, 1, and then expand it to n, that means x times y could be equal to a, okay? And prod a, z, b is the same thing, but means a times z could be equal to p, okay? Then the left triple product condition is you take the and of those two Boolean tensors and then take any on the 3, which is the a variable. So that means that if there exists any a such that x times y could equal a and a times z could equal p, then we'll say that x times y times z could equal p. Okay. Then you can also define the right triple product in a similar way. And the triple product possibilities are the and of those two. And then you, in a similar way, so, but you see, it might be the case that you have a template, but the left triple product possibilities are disjoint from the right ones, for example, then it's going to be not possible. Or also, more subtly, you can go backwards and sort of fill in some zeros and say that some possible products are not possible because of this condition. So you can then go backwards. And the point is that you can program all this stuff using PyTorch tensor operations, which then can be sent, if you like, to GPUs and done in parallel. Now, what about the structure of a proof step? Okay, a proof step consists of choosing a cut. So what's a cut? A cut means we choose some value xi, yi, and then a given row, the row is our prod tensor, generates a sequence of new positions, row 1 and row k. Every time you have a 1 in the column xi, yi, comma p. So in other words, all the times where it's possible that x times y equals p, then you say, okay, that's one of the possibilities. Then if there's k values, positive values in that column, that means that we're going to generate k new positions. Okay, so that's the typical case of a proof tree that we were discussing before. In some way, it's really quite the same as what I said before about applying the excluded middle on each of the statements x times y equals p, basically. And x times y has to be one of those possibilities, and we just divide into those possible cases. And then a proof, full proof corresponds to a proof tree where each node is decorated with a context, which is represented by a template. The root of the tree is the initial position, and then every time we make a cut, then we choose then that generates the nodes before it. Then you have to process the nodes, and then you have to decide whether they're done or impossible. When everything is done or impossible, then we're done. So there's a picture. So typically here, for example, if we did the cut on the cut question of what's 3 times 3, well, 3 times 3 could equal 0, or it could equal 1, or it could equal 2, and that generates 3 new nodes. Here up at the top, we said, okay, 3 times 2 was either equal to 0 or it was equal to 1. That generates 2 whole proof trees. And of course, the question here is, we'd like to choose the cut, so we want to choose which value x times y we look at in such a way that that we make it as the proof tree as small as possible. You're not supposed to choose one where there's only one possibility anyway, because you already knew that. Okay, so you choose anytime there's at least 2 possibilities. This has, if you're interested in this whole sandpile thing, it's kind of like an abelian sandpile in the sense that if we go back to the picture here, in the sense that what's happening on this part of the picture, on the left part of the picture, and what's happening on the right part of the picture are pretty much completely independent. So the size of a proof below a given node, that only depends on that node. It doesn't depend on other parts of the proof. Of course, you could imagine situations where that's not true, but that simplifies the theory, of course, a lot. And which cut you choose could possibly make a big difference in the length of the proof. And how we measure the size of the proof, well, there's different counts. You might just choose the active nodes, in other words, the interior nodes with at least two vertices below them, or you might choose you might include the undone or impossible nodes also. That's kind of a matter of taste and would lead to some slightly different results. So this is kind of a microcosm for the more general question of how do you choose a proof tactic to make the smallest possible proof. By smallest possible, of course, in the case of a proof, that means the size might be infinite in the sense that you never got the proof done. So the first question is to how to even find the proof at all, which means cutting the size of the proof from infinity down to some finite number. In this case, at least in our case, one of the good points is that we know that the proof is going to finish sooner or later. Once we've chosen all the locations x, y, then we're sure that we've finished the classification. We'd like to do less. We'd like to choose less than all of those. And so this is the objective is to minimize the number of, let's say, active nodes here. We chose active nodes as the measure just because it's an active node that requires the most computation, basically. So if you want to sort of try to minimize the amount of computation, I mean, you could also measure it by the amount of computation, I guess, also, but I'm not quite sure how to exactly define that. But in order to minimize the amount of computation, you really want to minimize the number of active nodes because those are the places where you need to do stuff. Okay, and then after we saw AlphaGo, AlphaZero, and so on, then that just motivates the idea of applying reinforcement learning to this question. And as I said before, it's local. So the size of the proof under a given node only depends on the cut that we chose at that node. But it's going to depend on what our future strategy of cuts is for those future nodes. That's why it's reinforcement learning. Okay, so now I think there's really, as far as I can tell, only one possible strategy, which is to try to learn the function, which is the number of nodes below rho, the value of a context, and then choose the cut that minimizes the policy question, which is the sum of the values below each of the new positions. Okay. Now, actually, it turns out to be a good idea, and we saw this, I think, in alpha or whatever, to actually have two networks. One is to predict the value, and the other is to predict the policy question. So in the policy question, the output is an n by n tensor that tells you the value at each x, y. Why do you need to do that? It's basically because calculating, if I can go back for a minute, calculating this thing involves calculating the positions, in other words, processing the positions generated by the cut. And so if you want to do that for every possible x, y, then that's a lot of calculation that wasn't really necessary. So you'd prefer to have the neural network give an estimate of that instead. Okay, that's what I said here. We have to process the results. Then it also turns out, for some strange reason, which for me is completely mysterious, that this also actually seems to work better for the whole reinforcement learning, machine learning aspect also. I don't know what the story was behind that, how that showed up in AlphaGo, for example, but that was their conclusion there, and just experimentally that just seems to be correct. Then we have a question of how to obtain the data. I don't really have an answer to this question. It's a difficult question. You may take a sort of a random choice of cuts at each stage and then prune or something like that and generate some proof positions. The problem here is that the proof tree is very, very imbalanced. So for example, typically if you do the first 10 steps and you get like 1,000 leaves after the first 10 steps, then maybe only 10 of those contribute to leaves down to step 20, but you don't know which 10 they were, right? And so at stage 20, at depth 20, only 10 of those original guys may have actually contributed to but some gigantic tree is down at level 20, and then that continues, level 30 and so on. So if you pruned it, if you took 10% of the, if you took, or even whatever, if you took 10% of the nodes step 10 at depth 10, you might well have missed out all of those 10, so you might just not have any data at all that goes down to level 20. That's like the basic problem here. And I don't have a solution to that problem. I mean, you just sort of have to try to make up a heuristic way of doing that, as far as I know. You could try to use the foolproof, but that's not really allowable in some way for the general situation. One possible idea was to to be running the foolproof and be training your networks at the same time as you're running the foolproof. Then you're of course treating the current type of proof question that's happening in that way. That obviously slows things down quite a bit. Yeah, I don't have any. This is I think is the main question really. Anyway, once we have a set of sample positions, then we can use an iterative procedure to train the value and policy networks. Just because in other words, you don't need to go all the way to the bottom of the tree to define the value. The value is just defined recursively by this equation. You can then use the policy network to determine the choice of x, y, and then use the value network to determine the pieces of the sum. That recursively generates the values of the value network for bigger, for higher up things. That's somewhat surprising, but it seems but that actually works. And then to train the policy network, once you have the value network, once you start getting the value network going, then the policy network is just trained by choosing some random sample of values of x, y, and evaluating on those things. You might say, okay, we should actually we should train on all of the values of x, y. For some reason, that doesn't seem to be a good idea. I mean, it was tried, of course, but it just doesn't work. It's better to just choose some random values of x, y. It's better to randomly choose a position, and for that position, randomly choose one value of x, y, and then try using that. anyway. Then for network architecture, well, this when I was first starting this, I was not very not very competent in network architecture. Doing network architecture is actually quite easy now with PyTorch. You just sort of look up a type of neural network, and you have to understand the documentation to figure out what's supposed to go in, and then plug that in. Then the training process is standard also. You have to use mini batch gradient descent. You would have to use Atom. I mean, if you start using things like transformers inside your, I mean, things like attention layers inside your network, then you need to use Atom type of gradient descent steps. Then what exactly sizes of mini batches? How much do you train on each mini batch and so on? That's just kind of a heuristic for me, an experimental question. So here was an example of what happened when we take not the full 451 case, right? The 451 case. Remember that this is really talking about semigroups of size 11. So that's actually bigger than what was known, at least in 2010. This was not the full 451 case, but it was one of the approximately 1,000 initial instances of the 451 case. But you can see what happens to the number of steps that you need at the first. If you just choose a random strategy, it's like 40,000. Then the number of steps goes below like 15,000. This blue line, the 15,000, is what happens if you sort of choose a heuristic kind of lexicographic order strategy. And these are the performance of the value and policy networks. So on the x-axis is the supposed true value. On the y-axis is the thing that the neural network is trying to predict. So you can see that the value network predicts pretty well. That's generally speaking often happens. The policy network has trouble predicting all that well, but kind of vaguely goes in the right direction. So it means that whichever xy you're choosing is not the worst one, probably. It's probably not exactly the best one either, but it's sort of a pretty good choice. These are the loss functions. I think I saw that on the slide, Roberta's slide actually. These are the loss functions. The blue and the green ones, those are the loss functions for the policy network, and the red and orange ones are the loss functions for the value network, which is obviously getting better more quickly. This little sine curve I was adding some kind of variable something some noise into the training process. This is a smaller case, a 321 case, so that means a size 7 nilpotent semigroup. And here you could actually get down. You can actually calculate the minimum possible number of proof steps, and the number of proof steps that are found by the machine learning system goes down to the minimum, but then it kind of bounces back, so it sort of bounces around that minimum basically. That's another question I think that's interesting. Why does it sort of bounce? Why doesn't it like just stop at the bottom? I'm not sure why. It does. Then let me just quickly go through this is just some different runs for like without taking the graded condition, just looking at all semigroups of size n. The number of steps starting goes down, up and down, up and down, goes down. Typically, nilpotent things of size 7. You could also talk about, you can make other conditions. I mean, you could just talk about general semigroups, but then you have a pretty bad case of this symmetry problem. So it's usually better to specify some type of properties. So a band, for example, where all the elements are idempotent. Here the proof steps start at 2400 with a random strategy and get down to like 1800. For bands of size 6, it goes down pretty well. It didn't actually change all that. It went from 44,000 to 32,000 steps after 10 rounds. I mean, typically these things will pretty much stabilize at very, very close to the minimum. Okay, anyway, so that's the end of that part. let me kind of quickly go through these. I wanted to add these slides, but we're a little late on time here, so let me kind of quickly go through these. But just say what
you can
was
have
the
more
question.
time. Don't worry about the time, Carlos. Don't worry about the time.
Oh,
yeah, you can.
Oh, well, how much time should I plan on? When should I plan on finishing?
I mean, yeah, would 10 more minutes be enough? I mean, if you need 15,
You mean
I don't know
like 40, like 3:45, for example. So I started a little late too.
Yeah, sure. That's why I'm yeah. So yeah, just I mean, it's now 5.
Sorry. Yeah, it's now 5.
Yeah. Yeah, okay. Yeah, like we usually have like 1 hour lecture plus half an hour discussion, but you can take some of the time
I
from the
see.
discussion.
Okay. Yeah. Well, I'll quickly go. Okay, we have a discussion. Okay, I'll quickly go through these other slides then. But what I did want to say something here, which is that some kind of curious observation that you get is that if you just choose, I mean, we can maybe go back a minute, right? This line here. Sorry, where was that? Right, this line here, this blue line, that was like what happens if you use lexicographic ordering. And it's actually quite good and kind of difficult to to do better. You can do a little bit better than that, but not so easy. So a kind of curious observation is that sometimes just using the standard lexicographic ordering and choosing the first available value of x, y, and for that ordering actually gives you a pretty good result. And it's maybe not all that surprising because we used lexicographic ordering also when we tried to remove the symmetry. So there's already some lexicographic ordering in the preparation of the initial conditions. So maybe not completely surprising that might be related. But we can ask, is there a way of doing that? So is there a way of fixing a global ordering on the set of pairs x, y? And we just, at each stage, we just choose the first x, y in that ordering. And then the question is, how would you go about trying to learn something about that? So I just kind of came up with a brief little possible process, which is that you predict a function. So you try to predict a function that tells you kind of the power of a certain collection of cut locations, but the power for general, not only for a specific, right? Because in our mode so far, each choice of action was depending on a specific location in the proof tree. But you could also say, suppose we want to make a uniform choice of actions that works for all possible positions of the proof tree. Then you have to sort of average over the possible positions of the proof tree and try to define what it means to be a sort of a good collection of cuts. And that's this function A of sigma. We can do some learning for this A of sigma. And then we can define the global value of A of sigma to be the sum of the local values of A sigma. I mean, for a given permutation, the global value is the sum of the subsets that you get by adding the locations in that sequence of locations along the way. And so here, this is the picture of what happens initially. So this curve is the A value, and so the global amount here is the integral, right? It's the sum. So it's the integral under that curve. And so the yellow curve is what happens if you choose the lexicographic ordering. And the green curve is what happens if you choose some random ordering. So you can see it's less good. And indeed, the random ordering gives you a worse time for the proof. Then you can try to maximize this global value. And to do that, what we do is because it depends on a permutation of the possible locations, we just make little changes of the permutations, which I was calling stochastic discrete descent. We make little changes in the locations and just try to make that value go up as much as possible. So here's like what happens as you randomly choose like 5 locations and make a permutation and choose the best of each permutation. The global value goes up and up and up and up and up and gets to 1065 in the end, and you get a new sorting of the indices. And now this is the same yellow curve that we had before for the lexicographic ordering. Now the global value is this green curve, and the area under the green curve is better than the area under the yellow curve. And that range of dots, that was the ordering that was chosen. So somehow we find some better order than the lexicographic ordering, and you can it does better. I mean, and so then in this way, well, I mean, let me just summarize here. Basically, the amount of time, the total amount of time for training everything. So doing the permutations, doing the training, this training of the A function, this stuff, the total time that you use to do everything. So the total amount of time it was taking to do the full proof without just using the random choice of ordering was 14 minutes. The total time it took to use the lexicographic order was 6 minutes and 26 seconds. And if you do the following thing, so you collect some samples, you learn the function and so on, you can do a little bit of training and then count up the amount total time, and you can do it in 9 minutes. So 9 minutes is better than 14 minutes. It's not as good as 6 minutes. If we did some more training, we can actually get to a better proof, slightly better proof than the lexicographic proof. However, the total time was 8 minutes and 50 seconds rather than 6 minutes and 30 seconds. Anyway, this was sort of a side excursion, which is sometimes but you have just to point out, you have to ask the question, did I save some total amount of time by doing this machine learning process? And often you didn't save a total amount of time, and quite the contrary, because you spent months trying to figure out your machine learning setup and so on, and then you spent a certain amount of processing time to train the machine and everything. And then of course, maybe it does the proof in a little bit faster time, but you would have just been better off taking a straightforward heuristic approach right away and forgetting about the machine learning thing. So that's say what I would suspect might possibly be the case in the case of set theory proofs also. So it remains to be seen whether machine learning is really necessarily going to improve the total global time situation. This little test here was an example where if you didn't know about the initial lexicographic ordering and just started with initial random ordering, then you can actually improve the total time by going with a training system. It's kind of like a fast training system like this. Okay, maybe I should stop here. I had a whole section about triangulations, but given
I would like to. Do you think you can tell us about it shortly? Say, I don't know.
Yeah. Okay. Well, let's go through triangulations. Yeah. I'm sorry. I was thinking that it was an hour and a half for the talk, but I think you must have told me, but I guess I forgot. Yeah. Anyway, so that was the semigroup project, and then when Elizabeth Gasparin, who some of you might possibly know, who does algebraic geometry and mathematical physics, she was visiting in Nice, and I explained to her the semigroup project, and she immediately said, well, why don't you look at the classification of triangulations? And as it turns out, this is a completely excellent question. So here's some pictures, I think this is Elizabeth's pictures or somebody in her group, of triangulations of a polytope. So you want to be able to write down all these triangulations. This picture is maybe a little bit misleading in the sense that the width of this rectangular strip is just 1. So here all the triangles go from the bottom to the top, whereas that's not what we're looking at in general. So in general, we're looking at a lattice polygon, so a polygon whose vertices are in the integer lattice. Then we would like to then you can put it inside of a square, for example. A polygon is a closed set of edges that don't cross each other and give you a positive area. And you'd like to look for lattice triangulations, which are triangulations such that the vertices of the triangulations are also on points of the lattice. And it's a maximal triangulation, which is to say all the triangles are minimal, that they have an area of 1/2. And the question is how to enumerate the triangulations of a given polygon. There's some mathematical physics motivation for this coming from toric geometry, which I don't completely understand, which is part of the problem why this is still in progress. But anyway, there's lots of them. In some cases, there are recurrence relations, for example, that allows you to say how many there are. So this is the number for a 6x7 rectangle. The number of triangulations is this number. We're not going to be finding that by computer, obviously, but we're not going to be, writing all those down by computer, clearly. A basic quantity which shows up in this theory is called the capacity, which is the log base 2 of the number divided by m times n. And turns out that's going to be a roughly, between 1 and 3 in around 2, basically. Non-convex polygons have less triangulations, obviously. And we're gonna look at an algorithm which was proposed by Ray and Seidel. Their algorithm was the case of arbitrary set of interior points, but we're going to use the points of the lattice. And they propose the following algorithm. Given a polygon, choose an edge. Look at all the primitive triangles inside the polygon that contain E as the edge. For each one of these, we generate a new polygon or a pair of polygons. And then we apply the algorithm recursively to the new polygons. And this is a dynamic programming question, which you might call divide and conquer. The semi-group question was also in that category of things. Some better algorithms were proposed, but we're just gonna, and it would probably be better to use the better algorithms, obviously, but we're just gonna use the basic Ray-Seidel algorithm as it's convenient for exploring our question. Okay, now if the new triangle doesn't cut P in 2, maybe I should just show you the picture. Okay, this, some people pointed out once I was giving a talk, said, oh, you missed, okay, so this is 2 out, so if we take this green edge, and what are the possible vertices of interior triangles? There's actually 3. There's the one on the left, the one on the right, and then there's the further one up and over by 1 again, which is not pictured here. But okay, if we look at the first triangle, the red triangle, then we just created a new polygon, a single new polygon, okay? Or you just remove that triangle from the polygon. If we look at the second picture, then we've created actually 2 new polygons because that red thing, that red triangle, that cut the original polygon into 2 pieces. Okay, so that generates 2 new pieces. So that's like that's our proof step situation, is when you have 2 new pieces. That's right. So either it doesn't cut P in 2, then I'm not sure about this subcases question, that I mean the number of new triangulations is containing that triangle is the same as the number of triangulations of the subpolygon. However, if we cut the polygon into 2, then an important point to notice is that suppose we get 2 new polygons, P prime and P double prime, then the number of triangulations is the product of the number of P prime and the number of P double prime. But the size of the proof is just the sum of the size for P prime and P double prime. Okay, so clearly if we have a product for the number of objects and a sum for the number of proof steps, there's a significant gain of time to happen here. And so you might say that the basic idea for the strategy is going to be to try to cut the polygon into smaller pieces kind of as early as possible. Well, strangely enough, so if here we took the 6x3 triangle, and I plotted for all the possible initial edges the number of steps of the proof. It turns out that this edge on the top edge on the left side of the triangle is actually the best with 1340, which is kind of unexpected given what I just said previously, which is you want to cut the thing in 2. You would think that one of these 2 edges in the middle on the bottom is the best. Those are pretty close at 1378, 1367, but for some strange reason, the one up here turns out to be the best. And then we're asking the machine to really learn all these numbers and then decide which is the best one. Okay, so let me just say that and put that there. These are just some numbers. Here I just sort of copied in a possible network architecture. We're kind of going to be combining linear layers, convolution layers, and attention layers. And we need to skip connections also. And so the idea of this sort of snake-like diagram like this is that you can have kind of a general flow with larger sets of with larger amounts of data flowing, then add some skip connections also. So I think there's a kind of general question as to how to design your network so that it has enough skip connections that you can that it gets started to prove your thing and stuff like that, and get started to find your quantity, but not too many skip connections so that it actually does some deep thinking also. Then here I'm just saying that again, kind of the training system is pretty much the same as we had before, with a value and a policy. This is a picture, so you should be looking here at the purple dots in the picture. Those are the number of proof steps. The other things, those are the loss functions, some of which are still pretty bad. And the proof gets down to pretty close. And in this particular case, you could actually figure out what the actual minimum number of proof steps was, which was 3308. And the machine found a proof in that minimum number of steps. I think I calculated that it was about 12,000 atom gradient descent steps to get there. However, it kind of once it finds it, it's not happy and it bounces back for some reason, which I don't understand. I think that's an interesting theoretical question. So I just drew a picture of like this is one of the strategy steps that's found by the machine. So it chooses the middle edge, then chooses the next edge here to give that sequence of triangles. So you can see that it really is sort of applying the strategy of trying to cut the polygon in two. Here, our initial polygon is a 3x3 square. So this is one of the branches of the tree from the top down to the bottom. Showing you what the strategy looks like. So you can see that it really is applying the strategy of like trying to cut the polygon in two as much as possible. And in some cases, a human might have found a strategy somewhat similar to this one. I don't think we would have thought of that upper edge on the left as the best edge to start with. So doing this, you actually can find pretty quickly strategies that are going to be better than the human strategy. And again, using what I call alpha, etc. You do this by using a policy network and a value network, which are based on the same kind of idea. Here again are pictures of what the value and policy accuracy look like. As before, the value network gets to be pretty accurate and the policy network not very accurate. If we start putting attention layers inside the neural network, then you really need an atom gradient descent operation. This is just sort of, these are pretty much the same as for the second group. That's what I'm saying. I mean, I think, once you get the whole setup going for set theory proofs, it's also going to be pretty much the same. Here was a different thing, which is we try to predict the actual number of triangulations rather than doing the proof for the triangulation. And this is also another somewhat strange thing that's happening, which is the number of triangulations in this case is 46,456. The purple line is the prediction of the number. The network just has a hard time settling on a predicted value of that. And it kind of bounces around a lot, kind of globally centered upon the correct value. But again, what we're trying to do here, maybe I should, this is a fully recursive definition of the value of the number of triangulations, which is to say, it's just trying to predict if we know the number of triangulations of a given polygon, and then we look at some step, some Ray-Seidel algorithm step, and suppose we have our network prediction of the number of triangulations for the subpolygons, then you just add those together to get the number of triangulations, or multiply in the case of two polygons, to get the value for the bigger polygon, and then you just train using that recursion thing. So you never actually count triangulations of anything. If this worked well, it would be a way of possibly like trying to predict numbers which are much bigger, like the one we saw before. Doesn't seem completely clear that that's actually going to be all that functional. As I said before, there's some stuff about symmetry of a polygon. In cases where there's some symmetry and you want to use a symmetrical thing, the attention network has some nice symmetry properties that allows you to code in stuff where you don't need to make a choice, basically. Then these last two slides are just about like what may be coming next. so like the next step for me at least is, in the case of set theory proofs, is to start off by trying to get some kind of rudimentary proof checking program written in PyTorch, which is different from like Rock or Lean or stuff like that. So there's a number of different reasons for that. One is to go as fast as possible, where I'm personally not all that competent at programming. So, but if you're doing your stuff in these parallelized languages, then it automatically goes fast, even if you're not doing such a great job of programming. And kind of similar to that is that it supports parallelization kind of automatically. You don't need to know how to do that. It just automatically parallelizable. It just means that it's doing your tensor calculations, whichever in whichever order it seems to think is best in order to put them onto the different processors. And so the user doesn't actually talk about that, basically. Similarly, we're talking about being able to treat large batches. So instead of doing a single proof at a time, which is the case of one of the typical proof systems, you might want to be able to do 1,000 proofs at a time, for example. And also, in order to interface with any kind of machine learning question, it's going to be easier and faster to pass the data from between the machine learning and the calculation part if they're both written in the same language, basically. So that's like the next step. Question in terms of data, in order to do this, we're not predicting necessarily that we need a lot of training data questions, because as we saw, just a single triangulation, for example, just triangulating a single polygon actually already gives you enough training data to train the machine, basically. So you should probably be able to train the machine on just a single proof question, for example. And in any case, a small number of proof questions that come from a set development set theory. Anyway, so that's the current status. So maybe I'll finish then.
Okay, so thanks a lot, for the talk. And now it is time for questions and discussion. So let me start actually chronologically, but I have a few questions, and perhaps it may be nice to ask them chronologically. So you started to work with the now called Rock in 2003, okay, right? Like you have something on your website, 25 years ago, say.
Yeah. Well, around 2000, maybe.
Yeah.
My wife's thesis director on the Yershowitz in Nice was working on that, and we were sitting around his pool, and I was saying, "Oh yeah, I would like kind of because of Pfefferman and stuff." So, "Oh yeah, okay. I'm interested in computer theorem proving." He said, "Oh yeah, we know how to do that." And I was going, "Oh really?" So then he started explaining that.
Okay, so I wanted to ask you somehow how it was. How did you see it back then, and how do you see it now somehow to compare those two moments in the...
Well, okay, so there was always a big question about what kind of mathematical foundations to choose, because if you've worked with computer formalization methods, typically a group is like a record having a type, which is its underlying type of the group, and then having an operation, A arrow A, maybe an identity element, and so on, and then having some axioms and stuff like that. So typically, a typical mathematical object is expressed as some type or some collection of types, plus some operations, plus some axioms, and that actually works pretty well, basically. The only problem is that you tend to get, sooner or later, you tend to run up against these problems of transport between types that are equal. And that was kind of the reason why I became interested in trying to just do everything using set theory, basically. That's kind of my own viewpoint. It's kind of a contrarian viewpoint, because the type theory people just like to use straight type theory. You can deal with the whole transport question within type theory. It does seem to lead to some difficult, pages of stuff, basically. But you know, it's kind of a question of maybe of taste or something like that. Then you know, but let me say it. So in our discussions about this, which was with Andrei Ischowitz and Marco Maggiesi, if you might know, for example, and other people, we were very heavily influenced by Benjamin Werner's paper that was called "Sets in Types, Types in Sets," I think, or vice versa, which explained how in type theory was explained the mutual interpretations between the kind of classical viewpoint on type theory and Zermel-Frankel set theory, basically. So the idea was just, okay, let's just kind of take that as a given, and then sort of say, well, you could either start with work with types or you could work with sets kind of interchangeably. That was the viewpoint at the time. So then I mean, the development I was doing ended up being sort of set theory related. Then of course I wouldn't say that at the time I was going, oh, we should do machine learning, because I didn't know what that meant or anything. I mean, in retrospect, you can see that there was clearly you could sort of clearly see that there was a need for that. You know, once we started hearing about all this machine learning stuff. I wouldn't say at the time that I was saying, you know, we should have to be able to do that. But I mean, I would say that at the time it was kind of clear that you needed some kind of automation for the proof process. Basically, because when you're doing a set theory version, then you've removed a lot of information that you get from the type theory. The type theory tells you that certain elements are elements of certain sets, basically. And that's kind of that's the positive and the negative. So it kind of allows you to transfer that information automatically through the proof, so you don't need to worry about it. But on the other hand, in some cases, you don't have that information. And then it kind of creates more of a problem to fill that information in. I mean, you know, a typical case is subtyping, basically. So, you know, if you have a group, you can have a theory of groups and so on. What happens if you have a subgroup? So if you have a subgroup, what is your subgroup? You know, is it a predicate on the group, or is it a type itself with an injection into the group? It's kind of hard to say. Whereas in set theory, a subgroup is just a subset of the group that's closed under multiplication. So what it means to be a subgroup is much clearer in an untyped version like set theory. And I think people have, you know, this has obviously been kind of one of the goals of developments of type theory, is to try to develop a type theory that has subtypes in it. But, you know, it runs up against foundational questions, questions that it makes things into, you know, not be strongly normalizable and that type of thing, whatever that means.
Okay. So now sure.
Yeah, so go ahead. That was the back then, you might say.
Yeah.
Then now it's like I'm sort of thinking, okay, but you know, as a result of that, it led to like a whole bunch of little stupid proofs that you needed to do all the time that were all pretty much the same, and I was just getting tired of that and kind of dropped the subject because it was getting to be very tiresome to do all those proofs, basically. And so like now the question is, can we go back and try to do that, but use machine learning to like fill in those proofs automatically?
Okay, so let me now move forward in time, like to this now to the what you told us about the semi-group, this classification, and that somehow you've adapted also these techniques for these triangulates, like this problem of the triangulations of Elizabeth Gasparin. Do you see somehow, are you working also on other directions? Like somehow I'm curious about how many like new projects as
I think the new project is going to be the set theory proof type of project. I wouldn't have the energy now. I mean, that's like going to fit into the whole Malinca question of doing proofs for mathematical texts. I don't think I would have the energy for a orthogonal combinatorics question, for example. So that's pretty much the next target.
Okay, so let me recall the questions are welcome anytime if someone in the audience has one. I wanted to ask you something that we asked already to someone who did close to a contribution like this. Like you do some combinatorics problem using these reinforcement learning techniques, you get some results, right? And now I saw your preprint on the archive in 2021 about this. I've seen that there is a small thing, a paper in a conference, I think, like a 2-page thing, kind of a summary. But say if a young mathematician now wants to get into this, that's something like, yeah, where do you publish it somehow? I don't know what your experience with this is like. You were not bothered to publish this thing about the semigroups, or it's just that you send it and then.
No, not really. Yeah, I don't know. I mean, I'm not sure how. I mean, yeah, I think for me, this is a very useful line of thinking. I think, but partly because it's leading to this question about how to do proofs in set theory. I'm not completely clear on whether we really need to know how to, do these classification things in any kind of like a bigger sense. I mean, for the triangulations, I think we would be thinking of writing that up as soon as we can figure out what. I mean, there's a thing about like trying to calculate partition functions and stuff like that in mathematical physics, which I don't understand. So that's still in the writing stages as a project. But there again, I think that like the defining, I'm not sure the mathematical physics literature really has a well-defined notion of partition function. Maybe it's a sort of a thing which they do on a case-by-case basis or something like that. So I'm also not a big expert on that, but so we're still sort of floating around a little bit in that direction.
Yeah, let me ask you some straight question, just out of curiosity. Like this preprint you had, you just were happy to post it on the archive, or is it like they've told us in this cycle before? If you send it to a maths journal, they will tell you, no, this is computer science. If you send it to a computer science journal, they will tell you, no, this is just very.
Yeah, I guess I would be a little bit afraid of that cycle. So I mean, I'm personally kind of happy to leave it as a preprint.
Okay. So you were.
I can see it's a problem. I can see it's a problem, but yeah, I mean, but that's kind of a question. Is like, why are we doing this machine learning stuff? I mean, for me, it's really the real question is to do proofs essentially. I think the real question is we would like to be able to fill in proofs of mathematical results, where the result is, kind of has an infinite collection of instances. I mean, doing something on a computer a priori, we're only treating sort of a finite collection of instances, basically. So in some way, I think it's the proof question where we're really getting. I mean, that would really be able to tell you something about, kind of an infinite collection of quantities in some way. Of course, I mean, it's not to say it could be interesting to have a nice small statement that about a large but finite collection of quantities, obviously. And there maybe there's a question, but typically in mathematics, we're talking about sort of infinite things. We want to make a statement for like all algebraic varieties or all something or other. In that case, I mean, I don't see kind of as a philosophical question. I don't see how. Of course, then there's a question of looking for counterexamples. So if you're looking for counterexamples, then obviously, one single finite counterexample will do the trick, right? It doesn't seem easy to, but then of course, then you have to kind of get lucky, so to speak. Yeah, that's why I think really for me the real question here is how to actually just do proofs. Proofs in the sense of a classical proof of a classical theorem and so on.
Yeah, but now that you mentioned this thing, okay, for any algebraic variety, so you say, okay, there are infinitely many. So, but then you can do it somehow through using like ROC or Lean or anywhere where those are implemented in the libraries, right?
Yeah, but I mean, I don't think people have succeeded in general in putting just regular math stuff into ROC or Lean or something like that. I mean, of course, it's getting going, and maybe LLMs will just do it for us, and we don't need to worry, and we can go home. I don't know. Yeah. But we would like to be able, but again, let me insist that we would like to be able to have a transparent and precise procedure, so the mathematician has some control over how the proof is happening. I mean, it's not just like send the statement to the LLM and it says, okay, it's true. It doesn't help really.
Okay, my next to last question. I wanted to ask you about this ROC versus Lean, because ROC has been there for a long time, right? And now, I mean, this Lean appear more recently, and from my ignorance, I can see in Lean they have this math lib where they say like a big chunk of the, say, undergraduate curriculum is formalized. Yeah. So how do you see like the comparison between the two? And I don't know if in ROC you have a similar amount of math formalized, and whether there is a way of merging those easily.
I think there should be a way of merging them. I think that, I mean, it used to be the case that more math was formalized in ROC, but now Lean has, I mean, people have been doing a lot. There's a lot of people who have been contributing lots of things. So probably more stuff is formalized in Lean. I think probably Mizar shouldn't be neglected in terms of quantity, although maybe the type of material is maybe somewhat specialized, sort of like real analysis type of material. But I think also they have a large library, as far as I know.
Why do you think
that in the future, I don't think there should be a serious problem in principle in translating from one to the other, really. It's usually kind of hard to figure out what the API is for the system. So it's not necessarily easy to extract the stuff. And here, I think, I mean, it might be the case that you also need the slow level proof search mechanism, because maybe some proof techniques that happen in one system are not necessarily easily translatable into the other. So instead of, you can think of, instead of translating math text into ROC or math text into Lean, you could say, let's translate Lean text into ROC text or something like that, as a somewhat similar type of a question, which probably requires, somewhat similar types of techniques, maybe. I don't think that's been done, as far as I know, too much, but maybe people are working on it.
Okay, and while as far as I see, like somehow ROC was there, you say like, okay, there was before more formalized in ROC, of course, then Lean appeared, and in my impression is that now somehow it took over, in terms of like more people using it and talking about it. Why do you think is that? Is a bit of just a trend, a hype, or you think Lean really offers something different to ROC?
I'm not a big expert actually here, but maybe Lean offers more of something a little bit closer to the kind of standard mathematician's viewpoint, where they don't necessarily care too much about like constructive mathematics, and don't really mind if they're using the axiom of choice more than they have to, and that type of thing. Possibly. I think ROC has historically been pretty closely tied to constructive mathematical questions, in the sense that you can. There's nothing. There's absolutely nothing that stops you from just putting axiom, the choice function, Hilbert's choice function, at the start of your file, and then that works perfectly well. But it's just sort of historically not something that people necessarily tended to do. And even there's things like setoids, which are different ways of talking about sets, which is a set with an equivalence relation, which is kind of like expressly designed for constructive mathematics questions where you don't have a quotient operation, for example. If you're in a constructive situation, you don't necessarily have a nice quotient operation, because you might need the axiom of choice if you wanted to choose equivalence class, or representatives of equivalence classes, for example. So I think, I'm not sure that's like, it's maybe more designed for computer scientists than for like classical standard mathematicians. So maybe one explanation is that maybe Lean was sort of said, okay, let's, forget about that thing as I'm sure probably in Lean you can probably also do constructive mathematics too, but there could be a question of, you know, what the system is like designed to be most efficient in doing, basically.
Okay. And last question, I have to say I was surprised because the little I read, it seems like from the project I really thought like it had to do more like with rock, lean, and now somehow you finished the talk by doing like kind of apology of this different thing, which is more of this proof formalization method in PyTorch, like more something different.
Well, but I mean,
to that.
you know, if you find your proof in PyTorch, it's supposed to be easy to transform it into a lean or a rock proof. I mean, but you know, it's I mean, what I'm talking about there is really very closely related, I think, to the whole sledgehammer pipeline in Isabelle, which I'm not an expert on either, but as far as I can tell from what I've read, you know, in Isabelle you can install a sledgehammer tactic that makes a call to Vampire. Then when you have a proof question, you can it like try to transform your proof question into a Vampire syntax, send it to Vampire and ask for the result and get it back. And then if that works, then you get a proof of your thing. What I was talking about at the end there is kind of based on that type of a question, really. I think that people are looking already, obviously, at trying to, you know, use machine learning for that type of thing also, kind of intelligent sledgehammer tactics and stuff like that.
Okay, so yeah, thanks a lot then for sharing everything for your time.
Thank you for listening, everybody.
And we'll have the last talk of this year on the 27th of April. On the 27th, we will have Charles Pfefferman. So see you next time.
Okay, thank you.
Yeah, thank you, Carlos. Thanks a lot.
Yeah.